I'll start the recording. There it is. All right. All right. Good morning, everyone. Hopefully you can see my screen. And well, what's this? Let's see. I need that. Don't need this. I'll close this out. Sorry. Again, good morning. And we have a lot to go over today. On Monday, when the next time we meet, we'll have a visitor presenting to us, Kyle Keithis, who runs the Fab Lab stuff here. And he'll be going over some of the basics for how to prepare things for the laser cutter. But today we're going to take some of those initial steps, sort of going from some sort of three-dimensional surface in Rhino to a bunch of two-dimensional components ready to be laser cut. And at the same time, we'll talk about why that's important. And I'll start there. Let me just close that. Yeah, there we are. And I just wanted to, again, touch base with you guys on what you were looking at over the last 2 days with these videos that I gave you, right? So that makes it really easy for you guys to go back and reference some of those tutorials. They're already posted on YouTube. You don't have to listen to me do them in real time. Anyway, I thought this was a nice sort of summary, right? So here we're doing a number of different things. This responsive surface with trusses. One of the things we're doing, obviously, is generating a surface from a set of points. And so, again, we talked about surfaces, or we went over surfaces in those videos, talking about the anatomy of them and sort of thinking about how we can, first of all, there's some methods for how to create them and generate them, but then also some of the things we can do with surfaces afterwards, right? So when you think about, let's say, the shape or the envelope or the form of a building, oftentimes the form or the envelope is defined as a surface, right? And then we take that surface, that master geometry, and we break it down into lots of parts and components. Whether that's in Rhino or Revit or a combination thereof, that's typically what we do, right? So we make the shape, and then we start to overlay more complexity onto it, right? Like, how would we make it? What kind of pieces are composed of it? Where is their glass? Where are the frames to hold the glass? Where is their masonry? How many different masonry units do we have? Those sorts of things, right? How do we turn a corner? Where do we have openings? Where do we put doors? All those sorts of concerns usually are things that we do to surfaces, right? And I don't think that's a foreign concept here by any means, but I think it's worth saying out loud because that's the significance here. In this case, you are modeling, let's say, what would be the shape of a roof, and then populating that with a list of trusses again. So this came full circle with our project one, where now we could actually populate a surface with trusses, right? So we find the sort of latitude lines across a surface, and then use those as our sort of initial starting ingredient for a set of bow trusses. And then understanding that we can, we can change the shape of that surface, right? And so again, information flows from left to right. So as we change the shape of the surface, all the shapes of the trusses change along with it, right? So we start to make a much more complex, and by complex, I mean sort of smart model, right? Where we, as we start to adjust things and enter in more information, as ambiguity sort of lifts, and we sort of make more and more design decisions and engineering decisions, we can enter in those or adjust those variables, and then everything sort of updates accordingly based off of the dependencies and associations and rules that we made, right? So again, that's the value proposition always, right? Is to, how to do things smarter. And this time around, here in another week or two, once we start the fabrication process, we'll start to talk about how to make things smarter when it comes to performance goals and criteria that we set for our grid shell system. So I just wanted to sort of show this again. So again, here we're making a surface from a set of points, right? And those points, they change their Z direction, right? Based off of this attractor point, right? So, that point is something that we generate. It's fairly common ingredient in parametric models. right? But again, it's this idea of attraction or the distance or proximity to, you know, what we're influencing, the geometry that we're changing to this attractor point, right? Okay, so, and don't worry, you'll use attractor points in the future, no doubt. So whether it's for shape or patterning or whatever. Anyway, I just wanted to come to this, and I'm just going to go ahead and close that. I'm going to put this aside for a moment, but suffice to say, we'll be dealing with surfaces for the rest of project 2. So anyway, let's talk a little more about digital fabrication and planar fabrication, right? This idea of going from a 3-dimensional surface and actually turning it into a set of architectural components that can be fabricated out of planar materials, right? And it's not that we can't make doubly curved materials. If you think about, let's say, the automobile you drive, for instance, right? There's lots of curved, doubly curved, really sort of complex compound curvature, curved components, right? You think about the fender, you know, all of those sort of panels along the body, the interior, right? You know, some of those are formed out of metal, some are formed out of fiberglass, some are formed out of foam and other sorts of plastics. And you know, what's interesting about this is that the proposition here isn't that you can't make things doubly curved, right? But that when we do it for a car, right, there's a sort of how would you put this, a sort of scale of production to it, right? So in other words, it makes sense to pay, let's say Ford or GM or Chrysler, Dodge, or Fiat or whoever you bought your car from, you know, to sort of invest in the tooling to make these sort of really complex shapes, because they make them over and over again, right? So they do a lot of R&D, you know, over the course of a year in order to release the next year's models, car models, and then there's a sort of mass production side of this, a sort of economy of scale to it, right? Architecture is typically a one-off proposition, right? Every building is different. It has a different site. You know, the people that come together and put it together, you know, it might be a different architect, a different engineer, and a different contractor each time, right? Depending on who wins a bid and who the architect hires and all that sort of stuff. So in that case, you know, what typically happens is we start to approximate curved geometries with flat components, and some of these CNC technologies, in other words, automated computer-driven fabrication equipment, can help us do that effectively and without breaking budget. So again, this is I keep saying the word value proposition, but this really is a set of value propositions, right? So as you design, I think as you start to really become disciplined as an architecture student and then as an architectural intern, and then finally a practicing architect, I think you'll start to understand that essentially, you know, design is making a bunch of decisions with trade-offs, right? And it's not like there's a right answer and a wrong answer, but it's about negotiating and balancing a set of trade-offs so that you can make something meaningful, right? And so that's what I mean by a value proposition. How do you make decisions that solve 2 or 3 problems at once instead of creating 2 or 3 problems at once, right? How do those challenges and opportunities start to align? Becomes just as important as making a cool shape or form, right? In fact, I would argue it's more important than that. Okay, so without any further ado, maybe, let's see, slideshow. There we go. Try to get this up. All right, so digital fabrication, planar fabrication. Digital fabrication, or talking about planar fabrication, in other words, taking flat pieces of material and making something 3-dimensional out of them. We've done this in a number of different scales and different ways. I'm guessing a lot of you have done this at some point, try to make some sort of egg crate geometry, right? Notch geometry. Maybe in this case, it was out of cardboard, or maybe it's out of wood, or maybe you got something from the museum store somebody brought home for you when you were younger, you know, and you snap things together and slide things together, right? But it's essentially this idea of taking something large and 3-dimensional, breaking it up and maybe slicing it, or in other words, generating a set of components, right? And then laying those components out for fabrication, right? So that you can start to begin to think about the tooling and the production side of things, right? The equipment involved, and thinking a few steps ahead in that sense, right? Not only about how to make the components, but then how to deliver them, right? Will they fit on the size of a truck? That's oftentimes the limiting, that's one of the limiting factors for how large you can sort of make these chunks and modules that maybe get prefabricated in a factory before being delivered to the site, right? Will it fit on a flatbed of a truck that can go down a single lane of the interstate system? Or can it fit on an airplane? Or can it fit through a particular kind of doorway or whatever, right? So you'll find oftentimes that thinking a few steps ahead really comes in handy, right? When it comes to this sort of logistics game of moving things in and out and being able to transport them and lift them into place and clip them onto the right place, right? So the assembly, the transportation, also the fabrication, you know, it's one big sort of downstream loop, right? That you have to sort of take into consideration, right? I think once you start to understand that, you start to understand that every curve or line that you draw really has some profound implications, right? On folks that you never meet, right? But you depend on in order to sort of create a piece of architecture, carpenters and sheet metal fabricators and you know, construction workers that might be 100 feet up in the air with dust and wind blowing at them, trying to locate a three-dimensional point in space somewhere with a crane, right? So all of these sort of things happen, and you're controlling it. The stuff you draw, right? The stuff you model, the decisions you make, sort of orchestrate it all, right? It's really fascinating. And so I just want you to think about that as you go. Right, so here's another example of taking a sort of surface, breaking it up into components, right? Then taking each of those components, thinking about how they might be assembled, in this case, putting tabs in, then also adding labels and things like that. Since each one's different, each one needs a unique label, so you understand which piece is which, right? Otherwise, you have too complicated of a jigsaw puzzle at the end, you'll never solve it. So let's talk about some of these particular methods that we typically use. This is a craftsperson working on the hull of a boat, right? So you can start to understand this sort of wooden boat, this idea of contouring, right? So in Rhino, we have the tool called Lofting, which involves taking a bunch of sectional profiles like these structural ribs and then skinning in between them to create a surface. But in the boat or shipbuilding industry, right, lofting is actually the reverse process. It's taking a complex shape of let's say a boat hull, and then beginning to delineate and mark out those sectional cross sections for the componentry for, let's say, these ribs. It looks very skeletal, of course, because ships and boats, just like our buildings, have structure, right, and they have skin, and so. This idea of contouring or taking a larger shape and then slicing and dicing it with planes in order to define some shapes that can then be cut from flat materials. In this case, laminated woods and timber and things like that. But in other cases, we use plywood or chipboard, aluminum or steel, plexiglass, or other sorts of acrylics or other sorts of plastics, polycarbonates, for instance. Etc. On down the line, right? And so here's an example from the ATH Zurich, one of the best schools in the known universe in Switzerland. But basically what they did is they were looking at an exhibition to display a bunch of architectural models. And so they fabricated this sort of false landscape, right, to sort of run the length of a gallery space. What they did is they took a set of sections, let's say, of the landscape, and then lofted them together in order to create this sort of interesting sort of modelscape. And then took this sort of three-dimensional surface and sliced and diced it, right? So you start to see, I don't know if you can see the striping on the model here, right? And sometimes they just took alternating ribs, and other times they took the full sort of ribs to make a sort of complete lamination. So sometimes you can see through it and you have sort of gaps in between the structure, and other times it forms a really full, complete surface, right? Breaking them up, each one into a set of components, right? These were actually fabricated with CNC saws. So if you think about, let's say, a sort of KUKA robot arm, right, that can sort of knuckled and can move, and you put a spinning blade on it, then you can start to cut all of these bevels and angles. And then actually begin to alter the cutting angle as it moves linearly through the lumber, right? And so the results as they put together, right, you start to get this sort of interesting built landscape, right, that then suddenly receives these models And it sort of becomes this sort of interesting exhibition model space. This scales up, right? In fact, I don't know if any of you have been to Chicago. If you haven't, first of all, please go. It really is convenient. It's a great city and a great architectural city and a great urban environment. But there's some fascinating pieces of architecture there. And this is one of them. This is the Aqua Tower by Jeannie Gang, one of the best American architects currently practicing right now. She's absolutely amazing. This tower, each floor plate is different, right? So the edge of it is curved and each one is different. And so it's about taking this sort of three-dimensional shape, contouring it with a spacing of floor to floor height, right? In order to sort of give these shapes to the contractor for each of these custom floor plate edges, right? So what's interesting is they generated this form by looking out and trying to give each unit sort of 2 or 3 different viewing angles out, right? Towards the lake and then out and then inwards into the loop of the city, right? So the sort of downtown area where you can see things like the Sears Tower and the river and some of those other sort of famous skyscrapers and landmarks in downtown Chicago. But the result is actually quite interesting here, right? So, but again, you know, the floor plans don't actually change here and there too much, right? You can see the facade actually is inset and actually looks quite planar, right? But it's just those edges of the slabs, which basically create these sort of custom balconies for each unit, right? That's actually the sort of three-dimensionally customized parts. And what's interesting here is that you might go, how much did that cost? The question really is, how much extra did the developer get to charge for each unit based off of views of particular landmarks around one of the most famous cities in the world, right? And so when you get a lakefront view, right, or a loop view, or both, right, then you start to be able to charge a premium per unit, right? So in this case, it's about doing something really interesting and sort of taking a developer's pro forma, right? One-upping it to create value for your clients and the users, in this case, the tenants that would be leasing or buying these condos. And at the same time, making something really interesting formally in that stands out in what's already a very crowded and iconic skyline. So it's a really interesting sort of negotiation here between all of these sort of constraints and trying to get them again to align. In other words, to take challenges, make them into opportunities. And clients love it when you can do that, right? And the general public love this building. It's a fascinating icon, again, and a sort of skyline that's filled with all kinds of shapes and famous buildings. Right, and then thinking about way down in scale, right? This is a chipboard model that we made one year, right? And sort of taking these gyroid geometries and you know, really without a 3D printer, it's really hard to make something like this unless you slice and dice it. You contour it, right? You cut it up into a bunch of sections. You laser cut each section, and then you laminate it back together. You know, in order to create, let's say, a gallery piece. And you know, there's a materiality to this, right? You do it out of corrugated cardboard, right? The corrugations, right? When you look at it through one direction in the corrugations, it becomes, you start to see light and view through it. And when you look at it in the other, it's the other direction, you know, the corrugation, it's opaque. And so you can actually begin to play these sort of weird material games where you start to sort of take into consideration both the materials and the geometries and the fabrication tools all at once, right? Again, these would scale up. I actually hate projects like this where they try to make it look like you can just take a model and scale it up like that. It's not that easy. That's not a piece of architecture. That's really just sort of a caricature at this point without a lot of design investigation. All right. Okay, so that's one way to think about slicing and dicing, right? In order to get these sort of sectional shapes. And then, you know, maybe it's a sort of structural ribs, maybe it's a surface, maybe it's a set of floor plates or whatever, but you can begin to laminate them back up. Another way to think about this is a way that cartographers have long thought about our planet in particular, and that is to unroll. How do you take something that's doubly curved, like let's say the surface of the Earth, and unroll it into something flat that's understandable, right? What I think is fascinating about this slide is that these are different ways that cartographers have unrolled our globe, right, our planet, in order to try to understand and make maps, flat maps of our geographies. And what's interesting here is that there's a sort of, color-coded sort of how much distortion is involved, right? So in other words, when you take something doubly curved and you just try to flatten it out, let's say a globe, right, or a dome, it's really hard to do it without tearing, stretching, or otherwise sort of deforming and distorting things, right? And so it's an imperfect way. So you can see here, there's minimal tearing, just one sort of incision made in order to flatten this out, but then there's lots and lots of distortion. Here, they minimize distortion, but what that means is they had to sort of dart and add lots of incisions and start to sort of cut the curvature, the geometry in order to sort of unroll it, right? Okay. So there's lots of different ways we can think about this. One, right, is this sort of Frank Gehry way, right? Which is to say, I'm going to take something doubly curved, but then I'm going to post-optimize the double curvature into a set of single curved strips. So in one direction, you get this sort of crazy curvature. In the other direction, you see strips, and where they meet, you get these, you see the edges, right? You see these creases, right? So one way to think about this is to start modeling with something that's actually flat, right? So here was an idea, a project done at the AA, the Architectural Association in London, by students, grad students, where looking at something complex like this, what they did is they started with pieces of paper and then also pieces of sheet material like metal. And they started with something that was actually flat. When you start to twist and bend and curve things that are flat, you know that eventually you can always straighten them back out into something flat again, right? And so taking the generative logic of, let's say, something that's already flat and curving it, single curvature, became the generative logic to make something complex three-dimensionally with particular material and spatial effects, right? But then with that sort of built-in logic of being able to flatten it back out into components that could actually be made much easier and cheaper than, let's say, trying to make a bunch of double curved things, right? So this is actually, this is actually just a piece of paper. If you take a piece of paper and you just roll it like this, and then you connect the strips this way. Let me just draw here. Try my best with touchpad, right? So here's the unit right here. And so this is, again, this right here is just one strip of paper, right? That gets bent, and then instead of connecting these two edges, you just connect these edges, and then you connect this up with the next one, right? And so by doing these sort of paper bending and folding exercises, they're able to create something much more complex, right? They were sort of taking something very simple set of rules and very simple set of parts and seeing if they could do something really sort of counterintuitive and sort of making these interesting sort of new material systems, right? And again, you look at this and you go, that's crazy. But there's an interesting sort of set of performance criteria here, which is, there's apertures through this. So it could be dealing with ventilation, view, or shading, right? At the same time, you're doing something really kind of complex that almost looks like the fish of gills. It's very sort of biomorphic, right? Sort of zoomorphic in its shape. But ultimately realizable by very simple materials, right? So kind of an interesting sort of R&D that they were doing here in this particular grad program. Let me just try to clear out my chicken scratch here. Try to turn off these. Oh no, I might have to end the show here just to, oh no, let's see. All right, yeah, clear drawings. That was a disaster. All right, great. I'll just go back to this one. Restart this. All right. So anyway, you can see all these different variations of taking, let's say in this case, flat strip materials, right? Like paper and then maybe aluminum flashing and things like that, and then cutting them and then beginning to bend, fold, and twist them, right? And again, this scales up. So this is a model. Sorry, this is a scan of a book. Back when we used to get like physical books and we'd have to like scan things in. But this is from Frank Gehry's office. So this was part of the concert shell, sorry, in Millennium Park in Chicago. What you can see is that they take these doubly curved geometries and they basically work them into sort of singly curved strips. And so if they can make a model of this out of flat materials like plastics, like acrylics and acetates and papers, right? They're very confident that they can deliver the same sort of curvature, but at different scale for a particular budget. It's not always that easy, right? So you take a complex form, like let's say this is one of the earliest examples of sort of taking a sort of digital model and doing something spectacular with it. This is the Guggenheim in Bilbao, Spain, by Frank Gehry, right? So this is part of the envelope model for it, taking a sort of bunch of complex shapes and breaking them up into quads, and then breaking each of those quads up diagonally in order to create triangles, right? The logic here is that triangles can always be planar, right? And so if you break it up into triangles, then you have a set of planar components that you can use, and then it's faceted, but it sort of approximates a doubly curved sort of, a complexly curved shapes and forms, right? And then they're always looking for all these different ways to take these complex shapes and break them up into small shapes. This is an idea called tessellation, which we'll talk about here in a few minutes in more detail. But sort of how do you take a large shape and break it up into smaller pieces, right? There's certain logics to this. There's irregular patterns and then regular patterns, right? Each time, what they can do is they can take a shape and they can look at the curvature analysis. And so they can take a look at this and go, well, the blue will only cost us, because of the curvature involved here, right? This is a Gaussian curvature analysis. So the blue is mapped on there, orange is mapped on there, red is mapped on there. And so they can I think, start to do at least some quick initial calculations, sort of saying, well, all the blue areas, and they can get the amount of area that's shaded with blue, would cost $1 per square foot. And all the yellow areas would cost $5 per square foot. And all the red areas would cost $30 per square foot. And they began to make some back of envelope calculations in trying to post-rationalize and then optimize the geometry, going back and forth between two competing constraints, getting the complex geometry, right? And not losing some of that detail, but at the same time making it compatible with their budget, right? So again, it's about these trade-offs, right? Trying to find that sweet spot between two things that are at odds with each other, right? In some cases, right? Like, let's say budget versus geometry. Here's another way of thinking about this. Instead of unrolling, so we're thinking about curved and twists and bending, we can think about creasing and actually folding, right? So these sort of, I'm guessing everybody's had some sort of model or toy based off of this, right? You could, I think back and, they're great. They look pretty cool in theory, but they're always impossible to put together when you're like 5 years old and you only have like Elmer's glue or something, right? But this idea that you can take, something that's again, that's doubly curved, and actually convert it into a bunch of planar components that could be unfolded and then laid out, right? And unrolling and unfolding is some of the stuff that we'll start to do right away. In fact, I'll go over that later today in our demonstration, right? Okay, so let's look at some examples of this. Here's another student example, right? It's this idea of how to make a hexagon or honeycomb. And it's the idea that I can take a strip of paper, right? So this is a strip of paper right here that just has a fold here and a fold here and a fold here and a fold here. And when I put it back to back with another piece of paper that's folded similarly, but in the opposite directions, right? I start to make a hexagonal cell. And if I keep doing and alternating those back and forth, I can start to create a set of hexagonal cells, right? So let me just again draw this out. I think it's easier to see if you draw it, right? So here's a slip of paper, right? And if I laid out this piece of paper, it'd look like this, right? With a fold here and a fold here and a fold here and another fold here, right? And so if I think about these larger cells, here's a piece of paper, right? Or one sheet, just sort of folded over and over and over again, right? And then there's another one right here. Right. And then all I'm left to do is to pin these things together where they match up, where they made up, right? In order to create these sort of interesting systems. And so if you can take a surface and begin to populate it with, in this case, hexagonal honeycomb, right? then you can begin to actually take each of these and lay them out, unroll them, or unfold them out. And then you have a set of edges or lines in order to run the laser cutter to just ever so slightly to score the material so you can fold it. And then a set of shapes around the outside for the through cuts to cut out each strip. Let me again just see if I can. Oh, come on. Sorry. Try to clear out the. There we go. Sorry. For some reason, I'm losing my cursor here. Oh no, where is it? I just put another red dot there. It's going to really bug me, but oh well. Okay, back to this, right? And so the result, right, this sort of quick design build project that they did, making these sort of partitions that modulate space and light, and interesting patterning. Each of these cells, right, are hexagons, but each hexagon is different geometrically, right? And so as you start to model, let's say a sort of wavy, undulating surface, right, and you begin to create this sort of differentiated cell system, this sort of cellular hexagonal honeycomb, then starts to look much more natural and biological, right? And so, here's the pattern, and here was the information, right? So here's, let's say, one of those larger walls. Break it down into panels. Each panel can then be broken up into these strips, and then each strip can then be nested within whatever size of the material comes in, or whatever size of the laser cutter bed, right? And then each one is nested, and then these dashes represent the lines that were just scored or dashed, right, in order to create this sort of folds, and then of course then a sort of solid lines for cutting out the pieces, right? And then there's even labels you can see here, right? There's labels here so we can understand which piece is which, in what order they go in. And then you can also see there are markings here, right? So what happened is where these things made up with others, what they did is they used bolts for the to sort of connect them. And so what they did is they actually used the laser cutter to cut out the holes for the bolts, even though this is just cardboard, so they probably could have done that with a hole punch or something. But in that case, you can start to mate things up precisely, right? And so then you start to, it also helps the few people doing assembly to understand really quickly if they've messed up or put a one piece in the wrong place, things won't line up correctly. And so then they look at it and go, oh, I have piece A trying to go into slot B, should be slot C or something like that, right? So you can, again, begin to choreograph and even do a little bit of quality control through the design information, the fabrication information, right? And so you can start to see then with this as a parametric model, right, you can begin to generate all kinds of variations of regular patterning, less regular patterning, density, depth, etc., right? And so again, each of these two things is just generated from the same model, the same graph, just changing a few sliders, right, in Grasshopper. All right. Another strategy to think about again, or another way of sort of thinking about this is when you take something large, right, and let's say curved, how do you break it up into a set of smaller pieces, right? That can then be unrolled or unfolded or whatever, right? So this idea is this concept is called tessellation, right? In mathematics, sort of how smaller shapes make larger systems and nest together in order to create, something larger is called tessellation, right? We usually do the reverse. We start with a larger shape or form or surface, and then we try to figure out how to break it up into components, right? You'll see a lot of different examples for this. This is part of Federation Square in Melbourne, Australia. And so what's interesting about this is the sort of patterning here, right? Again, this sort of tessellation. Now it looks really complex and chaotic, right? I mean, I would argue that it does, but there is a logic to this, right? And basically what they did is they took and found the sort of optimum shape that both glass and sandstone and the aluminum panels or zinc panels that they were using come in, right? So they found one standard shape and size that all the materials they're going to use for the envelope would come in, like one sort of module. And then they figured out how to begin to cut those modules up, right, into thirds. and how to take each of those thirds and diagonalize them into triangles. And how those triangles, how you could take a sort of standard module, cut it up into a set of standard triangular modules, how those modules can then begin to be deployed in both repeatable and non-repeatable patterns, right? So they started to create their own sort of custom panels, and then starting to look at the larger system that those different custom panels could begin to create. So there is a sort of minimum or zero waste logic here, right? And there is a sort of repetition. It's just not easy to see because it's not a standard grid, right? But it's all based on this sort of triangulation and the repeatable patterns of it, right? That they try to make it look non-repeatable, even though it is. All right, and so there's a lot of information here to manage, both from the standpoint of making sure that that the fabricators could actually do their shop drawings and you could actually double check everything, but also then, you know, putting together this complex set of pieces on site, right? And that's not to be, that should never be lost on us when we design something, right? You know, somebody's reading a paper set of drawings, and they could be outside pouring down rain and knee-deep mud, right? Construction sites are usually holes in the ground. I mean, for a long time, right? They're dusty or muddy, and exposed to all the elements, sun, wind, snow, whatever it is, wherever you're at. So again, this idea of how do these things get put together on sites, it should never be lost on you, right? In fact, that's how we spend a lot of our time, is putting together those drawing sets in order to sort of describe that to people that we've never met before. Right? All right, and so you can begin to see the interesting resulting sort of spatial and light effects, though, right? Look at those shadows and lighting and the sort of patterning on the inside. Absolutely spectacular. You know, Sydney, every year, you know, at New Year's, right? Like Sydney has their opera house, right? Sydney Opera House. And you see all the fireworks, you know, celebrating the new year, right? In Melbourne, this is Federation Square is where that happens, right? So if you're ever in Australia and you see the New Year's being sort of celebrated in Melbourne, there'll be Federation Squares like New York's Times Square, right? Where everybody just sort of packs in, and it's actually amazing place. All right, another way of thinking about this, maybe less complex, but still with triangles. Triangulation here. This is the courtyard of one of the exterior courtyards of the British Museum in London, enclosed with glass to become an interior courtyard by Foster and Partners, Norman Foster and Partners. So the idea here was to, you know, create this sort of really great sort of vaulting shell, close this exterior space out with glass, so it can become an interior hall for receptions and other kind of spectacular events that the British Museum would host. What's interesting is that, you know, you have this sort of neoclassical 19th century or 18th, maybe even 18th century building and courtyard, right? And so it's all based on this sort of symmetry, but nothing's really quite symmetrical and nothing's quite square. And you know, when they actually laser scanned and measured everything was just slightly off. So nothing was quite symmetrical, and nothing was quite square and plumb. And so each of these triangles, I apologize for the pixelation here. I couldn't find higher res images of this, but I think it's an important enough and seminal project when it comes to these ideas that I wanted to include it anyway. Each of these triangles are actually slightly different. And so each of the struts in between the glass, right, is separate as well, or completely different lengths as well. And then what's interesting about this system is for each node, they made these sort of asterisk shaped nodes, right, that all of these struts sort of slide onto. And so each of these asterisks are also unique. And so you can see it here, right? Here's a sort of cutaway of what one of these nodes looks like. Here's a cutaway of each of these struts sort of fitting into each of these sort of asterisks, right? These nodes. You can see these asterisks, they're each different, right? Each of these nodes are different. They were actually, interestingly, water jet cut out of steel, right? You can see there's quite thick steel. So just as we can use a laser cutter to fabricate, you know, to cut all kinds of custom shapes out of, let's say, 1/4-inch material, you know, soft materials like chipboard or acrylic, right? You can scale this process and these methods up. Water jet cutters can cut through something like 12 inches of titanium. Like, it's ridiculous. And so, in other words, you can begin to see that each of these were unique in order to create this sort of the system, right? It looks like there'd be symmetry and in this sort of neoclassical building, this sort of elegant glass shell added to it, for a sort of glass canopy. But in fact, it's deceptively simple. It's none of these nodes and struts are the same, and same with the triangular panes of glass. Each one is unique and different, right? Had to be geometrically described, then had to be fabricated, cut, and then put back together on site. Interestingly, here's that process. Actually, that looks like a torch, so maybe it was plasma cut and not water jet cut. All right, another example of this. You can see a couple of examples from Frank Gehry. This is from Bilbao, Spain. And this one is a bank building in Berlin, actually not too far from Brandenburg Gate and Tiergarten. But in this case, you see glass, and you see the glass, the rectangular panes of glass have been sliced in half and diagonal, right, into triangles. And so, again, the triangles can be flat and planar. And so that really helped them out when it came to, again, making something that looks curved, but out of flat pieces. Same thing here, right? These are all triangular pieces of glass. So each of these panes of glass are planar. Even though, as they're composed into a larger system, the system itself isn't planar, right? It's doubly curved. Here's, I think this is, I forget what the name of it, 655, or it's the street address, St. Mary's Axe. In London, they've nicknamed it the Gherkin, right? But it was originally called the Swiss Ray Tower. I don't think Swiss Ray, I think they sold it. But this idea of taking triangles, what Foster and Partners figured out, and I think really smart way, is that if they can find different ways to do the triangulation, but with diamonds or quad shapes, right? Then what they've done is they've managed to approximate the same shape, but with half the number of components, right? So in other words, instead of making two triangles here, if they could figure out a way to do it with these chevron or diamond shapes, right, these quads, then they've minimized, they've halved the number of actual components and halved the number of joints, right, and gaskets and whatever else that are required to sort of join these panes of glass together, right? And so there's this, again, it's sort of arms race for sort of thinking about geometry and doing more and more optimal and intelligent, smart things with it, right? Here you can see, again, flat planes of glass. In this case, this is a Frank Gehry project in Prague, Czech Republic. If you've ever been to Prague, it's a great city. If you're not, you need to go to Prague. It's a nice Baroque city in Bohemia. But what's interesting here is you get these planar sheets of glass, and the whole idea is that they don't line up. There's no butt joint between the sort of edges of the glass, right? In fact, what they do is they shingle the glass, right? And so they purposely don't align, right, in order to create this sort of interesting texture effect, right? And this is basically just a rain screen. And so, as long as you sort of shingle things in the correct way, right, then you still get this thing shedding water, like, let's say, direct rain and things like that, and snow. Another strategy here is to think about how these things go together, right? These ideas of interlocking systems. And, again, I think back to when I was younger, and I think someone gave me one of these kits once, where you get these balsa wood kits, from a museum store, let's say, these dinosaur skeletons. Everything sort of comes in these flat sheets of balsa wood. You pop them out, and then you notch them together, so these ribs sort of have a notch in them, and they slide into a notch going in the opposite direction or perpendicular direction with the spine, and on and on and on, right? You can think about that architecturally, right? I'll just quickly blow through some of these, right? This was an installation put in, a spatial insulation put by the architect Bill Massey, put in the courtyard for PS1, which is an extension of the MoMA Museum, in this case in Queens, New York. Every summer they have a sort of warm-up event, and they invite a young architect to sort of populate the courtyard for a series of parties that happen every Friday evening. But what's interesting here is that these steel structure, these steel ribs, right? If you think about trying to nest those onto a flat sheet of, let's say, steel, and laser cut them or route them out, you'll have a lot of waste, right? So you break them up into smaller components that then can be that can be nested in a much more efficient way. But then all those shapes have to be put back together. And so when you look at this project, when it's no longer there, it was a temporary project, you would see that these ribs are actually a bunch of pieces put together with these puzzle piece joints, where then you have, like, let's say this length, and this length, space for the welders to come in and sort of zap it back together, right? It's interesting that same architect, Bill Massey, would create these sort of custom concrete walls. He would make the formwork for the walls out of styrofoam, and he would CNC route the styrofoam. And so, you know, inherently there's a sort of set size for the formwork. And then putting the formwork together on site, he would then puzzle piece these things, and then he would leave the impressions of the puzzle piece joinery in the actual wall itself, right? And so there's traces of how the wall was made in a really sort of lovely poetic material sort of way, right? That's unique to concrete and formwork for it, and casting it. All right, I'm just going to blow through this really quickly, but this is similar to what we're going to do for the demonstration, what you'll do over the weekend with the script that I give you, right? You'll take a surface. We'll have a particular set of surfaces for you to look at, and you're going to run a script that will give you a sort of bilateral grid, right? Sort of two-way grid, two-way set of ribs that can then be laser cut and then notched together, right? And so the end result will be a set of ribs that you can, you know, again, sort of nest together, take the laser cutter, cut things out, and then start to notch things back together, right, for assembly. Later on, we'll take each of those cells and we'll populate each one with a sort of custom shade component that you'll develop. All right. Last thing I want to hit on here, for second to last thing, actually, this idea of nesting, right? This idea of yield, of trying to minimize waste, right? These are all a bunch of components, right, to be laser cut, and you can see that they're nested together to try to minimize the amount of waste, right? So all these offcuts, right? All of those things, you know, if they're odd shaped and really small, they're just going to be thrown in the trash, right? So making sure that you nest things out to get the most yield out of your materials. In fact, here's a set of 18 by 32 sheets where I took a bunch of two-way structural ribs and nested them in order to try to maximize the amount of material yield and minimize the waste, right? So where I do have some offcuts, it's small, right? I'm still getting a yield of 90% plus. And then where I have big spaces, right, I try to create shapes that I can use later on, right? So the offcuts are something that can be stored and used later, right? They're not some sort of really funky shape that are impossible to use with anything else, right? Okay. Last thing, right, is to think about the assembly of these things. And this is where, you know, maybe plan, section, elevation aren't as useful as sort of thinking about, you know, other sort of three-dimensional complex things that where each part is different, right? So I think about model airplanes and model cars and things like that I used to do when I was younger, right? But starting to think about architectural drawings that are kind of like exploded axons and talk about these things almost as if you bought this as a kit from IKEA, right? Which is another flat packed sort of set of parts that you then put together, right? So that these things can be assembled. All right. And so that's part of what we'll be doing with the representation at the end of project 2. You won't be doing perspectives. You'll be doing these sort of drawings where you're showing the pieces, you're showing the performance, and then you're showing how things go together, right? In this sort of popular mechanics exploded engine sort of way, right? Each of the parts and how they go together, right? Like an IKEA drawing or something, right? Okay. So you can start to see some of these examples from architecture, right? Sort of the results and then the drawings, right? Each of these pieces, you know, are very specific. They go together in a particular way. There's the assembly, and then there's the result. All right, so without any further ado, since we have about 20 minutes left, that's perfect. I'm just going to pull out my mouse, and we're going to do some quick demonstrations. I'm going to go through the workflow that I'm going to ask you to go through over the weekend. Okay, and again, I've kind of tried to make the Canvas page a sort of checklist for you. So if I go to the Canvas page for the day, 6th of October, first of all, there's 2 different files I want you to download and use. Okay, so make sure you do that. And then above this, I'll have the video from the day. This video that I'm recording. As soon as it's uploaded to YouTube, I'll post that here as well. okay? But then you'll see that there's instructions for what to do over the weekend, right? And there's also a video, a YouTube video on I want you to watch over the weekend. Be prepared to discuss, right? So take some notes, okay? All right. Akim Menges is a professor at the University of Stuttgart in Germany, and he does some amazing work there, sort of applied research, architectural research with a lot of industry partners and a lot of funding in investigating sort of non-traditional material systems. And so you can start to see some of these emerging technologies, emerging materials slowly being absorbed into architecture. And he's one of them, the people on the vanguard of really trying to think about, let's say, things like materials like carbon fiber, and how those begin to reshape the way we think about architecture, right? So this is one example. And so I want you to watch this video over the weekend, and just, again, try to carve out, I want to say it's, it's under an hour, to carve out the time and try to enjoy it. There's some impressive work in here. So if you're, really, not only a lover of architecture, but almost a junkie, like an architectural junkie, then, just pop some popcorn and sit back and relax and watch this thing. Because there's some of this stuff, it's like architectural porn. It's just ridiculously sweet. You just looking at it and you're like, wowie, like eye candy out the wazoo. It's just amazing, some of the things he does that seem impossible architecturally, and yet he's doing them by simply looking at material properties, looking at digital technologies, and sort of putting them together. And so rethinking how technology again is sort of helping us reshape architecture, right? You'll find that over the years, right, the architecture that we study is usually shaped by the technology at the time, right? So you think about what things were made out, what buildings were made out of and how they were put together, right? You start to understand the patterns and the sort of material and the larger culture that architecture was sort of conceived and built in. And so our era is one in which we're constantly being disrupted by sort of ongoing digital revolution, right? And so I think it's just again to be very conscious of that is an important thing, right? These things are constantly the landscape, the design landscape, and the tools that we use, the materials, and how things are put together on site. That landscape is constantly shifting underneath us, right? I just had a buddy, and he was in town. He was speaking at a roundtable and giving a presentation at I think at a realtors convention here in Las Vegas at the convention center. But it was all about the automated construction site, and he works for Boston Dynamics, a robotics firm. And it's interesting that a firm that's doing a bunch of Department of Defense work on robotics is now looking at how their robots can actually reshape the construction site of buildings, right? So, there's flying quadcopters measuring and photographing and scanning the building and its progress, lifting things, delivering things. There's pack mule, four-legged robots delivering things in and out, doing tasks that are either too repetitive or too dangerous for humans to do, et cetera, right? So I could give you a whole lecture on that, but I won't do that. All right, but you can see here step-by-step instructions. So the first thing you're going to do, right, is you're going to open up this Grasshopper file that I give you called shell surface classifications. All right, and what it's going to do is it's going to show you where I got these two surfaces. So I'm just going to create a new file just like you would do, and we'll go through this workflow step by step. File, new. Just create a new Rhino file. Right, I'm going to pick small objects. I'm going to pick inches. Really important, right? And I'll create a new file. Now, if you've created a new file and you're not sure what the units are, you want to double check and make sure that your units are set to inches. And I'm going to show you how to do that as well. Okay, so if you're in Rhino and you want to double check your units, the way to do that, and where most of the options are in Rhino, is to go to the Tools pull down, and down at the bottom of the menu that pops up is called Options. Okay, so Tools pull down at the bottom of the menu that pops up, Options, and it'll bring up a box with more settings than you ever cared to play with. One of these options will be units. I'm just going to plug in my mouse while I'm thinking about it here. Start to use that. There we go. Units, right? I'm just going to double check. Model units are set to inches. If they're set to millimeters or meters or whatever it is, right? go over here, set it to inches, hit OK, right? All right. Just want to make sure things are set to inches. That's really important because we're going to be making this stuff out of chipboard. We're going to be very precise about material thickness and making sure things fit inside the laser cutter, right? And that each of these are the same size and scale. And so making sure those units are set to inches is really, really important. If it's set to feet, you'll be off by a magnitude of in scale of 12, right? And if you're in millimeters, it'll be like, you'll be off by a magnitude of like, I don't know, something ridiculous, 25 or something, but in the reverse direction, you'll be way too small. So again, just make sure those units are set, okay? Then I'm going to go ahead and open up Grasshopper, and I'm going to open up the file called Shell Surface Classifications. In this file, we're doing something similar to what we did before, what you saw before in some of those videos you watched for the day, right? And that we're making a surface from a set of points, a grid of points. But in this case, we're making it from a different set of points, a different grid of points. I don't know why this is suddenly not responding. I just want to pull up the perspective view here so you can see it a little easier. Sometime today. Okay, whatever. All right. And so what I've done is in Grasshopper, I've generated a surface from a grid of points. And let's see, where is it? There we are. Okay. Grasshopper disappeared. I just have to minimize, maximize Rhino again. So what I'm doing is I'm saying, I'm creating a set of X, Y, and Z coordinates to make a grid of points. And for X, I'm just using a set of values that step from 0 to the max, in this case, 0 to 4 pi. Right. And then for V, I'm making a set of coordinates, a set of numbers, a list of numbers from 0 to 4 pi. So I use that as a range, right? And then I just divide the range X number of time to get, let's say, 28 values between 0 to 4 pi. And then, but for Z, instead of using 0, I'm taking the cosine of each of these U values and the sine of each of these V values and adding them together, right? And so what I get is a Z value that sort of steps up and down and oscillates like a sine wave, like a sine curve, but in 3 dimensions, right? So now I'm making this sort of sine or cosine wave surface, right? So I plug this expression in to the expression editor with my U and V values. I plug these in for X, Y, and Z. I get a set of points, right? I take this grid of points and I make a surface from a grid of points, right? Then I take this large surface and I just take one little patch of it, right? So I tell it, I just want the sort of patch or the parcel, right, along this surface that's between, in the U direction, between the U equals the 0 and the 0.25 sort of latitude lines. And then in the V direction, the patch between the 0.3 and 0.7 longitude lines, right? So in other words, I'm giving it a border. And inside of that I get a quad, right? A patch of the surface, right? And I do that over here for a different part, right? Okay. So just like I can sort of snippet or sample a portion of a curve by giving it a minimum and maximum, right? A sort of a first T value and a second T value, right? Here I can sort of differentiate, like almost like a Jeffersonian grid on a map, right? Sort of 2 latitude lines, 2 longitude lines, and then sort of the quad in between those four lines or curves in space, right? So to sort of break up the surface and get one sort of checker in the sort of larger checkerboard. All right. And so your first task is to just sort of look at these and sort of say, okay, I can pick this one, or I can pick this one, right? So this one, the concavity is going in the same direction in both U and V. It's sort of downward, it creates a sort of dome-like shape. This one is more like a groin vault, right? So the concavity is going upwards in the V direction and downwards in the U direction in order to create a saddle geometry. They're still doubly curved, each of them, but there's 2 sort of different types of surfaces, right? You're going to pick which one you want. And then depending on which one you pick, you're going to just right click and bake that into Rhino. Okay. Now everything will be just the right scale, right? So, I just, the rule of large numbers here, roughly half of you will probably pick this one, roughly half of you will pick the other one, right? It's not always half and half, but it's your decision, whatever what you want to pick, right? But let's say I pick this one, boom, right? First step done, right? So I go to the instructions, right? Now I've baked in my master geometry for my own grid shell, right? And I've already double checked my units, right? Now I'm gonna run this Rhino script, okay? All right, let's take a look at that Rhino script really quickly. I just showed you a sneak peek of this the other day. I'm gonna go to the tools pull down, Rhino script, edit. Okay, that brings up the monkey Rhino script editor. Of course, it's named after another animal. We're in Rhino, we have grasshoppers, we have monkeys. What else? Pythons, right? So whatever, right? But what's interesting, right, is that you're not going to have to actually read this or write this, but I'm just going to show you what's going on here. First of all, right, this is a script that one of my buddies wrote like a long time ago, 2005. So he doesn't mind if we use this as long as we don't distribute it. We have a set of variables that are defined, right? Really right off the bat, it says, okay, here I have a variable called source surface. There's a method in Rhino called rhino.getObject. What it does is it puts a message in the command line asking you to select a surface to populate with tiles. And so then it makes you, or asks you to select a surface, right? Then again in the command line, it asks you for a number, for the number of divisions in one direction, the number of divisions in the other direction. Then asks you for a height or depth for each sort of structural rib that it creates as it divides the surface into checkers. And then it lays all of those ribs out flat on the XY plane and asks how the spacing between each of these ribs so that you can try to avoid collisions and sort of, you know, when you're sort of dragging these things around and selecting them on your screen. It also asks for a material thickness for the notches, right? And it does all of these things for you, okay? So what I'm going to do is I'm just going to go ahead and click this run script green triangle. And okay, so first things first, it says select an object to populate with tiles. So I'm going to go ahead and click. It says enter the number of tiles in the U direction. I'm going to pick 20. So I'll type in 20 in the command line and hit enter. Enter the number of tiles in the V direction, right? Okay, so again, I'll probably pick the same number, in this case 20. Now it says the height of a strip or the depth of each sort of rib. I'm going to pick 0.25, maybe a quarter of an inch. Enter the X distance between onward ribs. I'm just going to pick something large, like 10 inches. And then between the Y distance, right? So between one set of ribs and the other set of ribs, like the distance, I'm just gonna pick 30. I just don't want them to overlap. So I'm just gonna hit enter. And then finally, the material thickness. You're gonna be applying or buying and making these grid shells out of one ply chipboard, which is 1/32 of an inch thick. So 0.030, right, is the nominal thickness. So 0.030. I'll just type that in for the material thickness. I'm gonna hit enter. And now it's going to do a bunch of stuff in the command line. It's building my model. And now it just built it. All right, so I'll just go to shaded view. Maybe ghosted view. There we go. And we can see what we have here. Okay. First and foremost, right, we have a set of ribs. Now, not only do we have flattened set of ribs, right, but we have a three-dimensional set of ribs. So this will be important for your assembly instructions and your sort of exploded axon, right? So you can take this surface, talk about how it was created a set of ribs. Each of these three-dimensional ribs, let me just select these, yeah, right there, right? When I go to the properties, they're labeled, like, so you can start to see this is 0, U0, the first in the U direction, seconds, third, fourth, fifth, sixth, right? You can also see that they're labeled out of scale right here, right? So this is the V direction, 0. This is the U direction, 0. I divided 20 times, so I should have 21 ribs in the U's and 21 ribs in the V's, right? There we are. All right. Now, likewise, let's just take a look at one of these ribs. I have the outline of the ribs, right? And they're on a layer called cut. Maybe, let's see. Oh, they're on the V-strips layer, right? Then I have the notches, right, that are basically just boxes on the cut layer. And then I have this sort of zigzagging thing called the score layer, right, where I can actually let it sort of slightly score the chipboard So just to make it a little more pliable so I can bend things into place later on when I'm trying to sort of fit all these things together, okay? All right. So what I want you to do is I want you to run the script at least 3 times, each time sort of creating a new, do it in a different file so you can keep all these things straight. You don't actually mix up the ribs from one, let's say one version to the other. But looking at the sort of density, right? So looking at like how many times you divide, right? Do not divide more than 20 times, right? Because if you think about that, that's going to give you 20 cells in one direction, 20 cells in the other direction. 20 times 20 is 400. You have 400 shading units to fabricate. That's a lot, right? It needs to be at least 10 divisions though, right? So in each direction. So somewhere between 10 and 20, right? You can, again, run this script. It only takes a few seconds each time, right? In order to sort of look at what you get and make a decision, right? Like, what do you want, right? You could do it 12 times or 15 times or 20 times or 10 times, right? To sort of look at that density and the spacing, right? And pick something that you like, right? But I will say for the U divisions, the V divisions, it needs to be, at least 10, no more than 20, right? I'll just give you that range to work within. That'll help you and save you some time later on, okay? So I did 20 at that point. I'll just pretend I didn't do that for a moment. I'll just undo this. Let's say I want to go back and rerun this. I'm actually going to pull this out over here so it's not clashing with my my ribs, my unrolled ribs. I'll run the play button. This time, instead of 10, I'll give it, or instead of 20, I'll give it 10, right? And 10 in this direction. To hide the strip, maybe I'll go with maybe something a little deeper than 0.25, maybe 0.375, right? That's a 3/8 of an inch instead of 1/4 of an inch. Enter the distance between strips, sure. I just did 1030.030, right? And I think what you'll see here is that things are going to be, slightly different. I have fewer cells, fewer ribs. The cells are larger, right? But then the ribs are a little deeper, right? So again, I wouldn't go deeper than 0.5 or maybe 0.375. I wouldn't go much slimmer in depth than 0.25 or 0.2 maybe, right? Because as soon as the material, the material has properties of the chipboard, sometimes you push it a little too much and it just snaps or rips or tears. So you don't want to tear your pieces after you've painstakingly laser cut them. There's a couple of other things here I want you to think about, right? So we have these sorry, let me just zoom in here with this tool, right? Sort of recenter the rotation. So we have these labels, these markings, right? They're out of scale. They're not in a good place. And they sort of have thickness to them. So there's a lot more redundant duplicate sort of scoring that you need to do for this. So one thing I would recommend you do is go through each of these ribs. And there's only, depending on how many cells or divisions you do, anywhere between 20 and 40 of these. It's not that bad. You can go to the text object tool. I'm going to say, okay, I'm going to make a height in inches of 0.125. So I'll make this really small, 1/8 of an inch. I'm going to use a particular font called SLF RHN Architect, right? That's a single stroke font. So each letter or number is only one sort of curve. It doesn't have thickness to it. So it'll save you laser cutting time. And I'm just going to revise this. I'm just going to say V0. Just make sure it's at curves, engraving font, sure. I'm going to hit OK. I'm just going to place this in a very particular spot, right? Where maybe I want it exactly, right? This is going to be displayed. I'm going to put it right there so that in each rib, I'm going to put that, in the right spot. Then I can get rid of these sort of larger labels that not so elegant looking, right? These labels are the opposite of elegant, that's for sure. Go ahead and delete those. Right? All right, I get rid of some of this. Let's see here. For some reason I have the points instead of the curve selected. That's weird, right? I'm just going to go through and start to clean some things up for laser cutting. Another thing you might notice, and again, we can go back over this again on Monday, right? But you'll notice that these outlines are kind of exploded into polyline segment, into an individual segment. So we'll probably join those together into sort of closed polylines in order to, again, to sort of minimize the amount of jogging and traveling that the laser cutter has to do between cuts. All right, so but I want you to run this 3 times using different parameters each time, really sort of try to dial these things in and write down and note your parameters, right? Remember those. Those are important because we'll use them later on. We model this in Grasshopper when we start to put together our cells and our shading components. And so knowing the number of divisions you have and things like that will be really important. You want to make sure that when you design the shading components that fit on the ribs, these ribs that, that the ribs that you generated with the script and the component shading components that you generate in Grasshopper line up when after you fabricate them. So again, you can go through these step by step. If you have any questions, feel free to ask me. You always do. And again, watch this video. And thanks for bearing with me. I think we're fast approaching the end of I think this class ends in about 3 minutes. Okay. Are there any questions? Again, read these carefully. You can always go back to this recording, which I'll post and put at the top of this page in Canvas as soon as I can. As soon as it's done processing and uploading to YouTube, I'll get it up there. Okay. But there's some things for you to do over the weekend. And then when we come back, Kyle will tell us some more things that we need to do to these files that you generated in order to get them ready for laser cutting on Monday, right? So on Monday, he'll go through some things. And then I'll give you some more feedback on when you need to get some chipboard. We'll start to plan some things out ahead as far as signing up for times for the laser cutter, et cetera. Okay, so next week, a lot of things sort of can come together. All right, great. All right, I'm going to stop sharing and stop recording.